Yesterday, we looked at radioactive decay. We looked at alpha decay and beta decay and how one element can decay over time and turn into a different element. We also looked at how gamma radiation is given off as this decay happens. And today I want to take just a little bit of time to look at how these radioactive isotopes can be useful in the field of science. One of the first things we're going to look at is radioactive dating. As these isotopes decay over time, there's a definite known time for how long it takes the isotope to decay. So we call that, let me get rid of that. We call that the half-life. So the half-life of a radioactive isotope is the length of time needed for half the atoms of a sample to decay. And that half-life is different for each radioactive isotope. They can range from, just a few seconds to billions of years. So what that basically means is that as this atom begins to decay, it takes a certain amount of time for it to decay. So the half-life is basically a measure of how long it takes for half of that sample to decay or to go away. There's a chart here at the bottom that gives you the half-lives of some common radioactive isotopes. You can see that polonium is like a fraction of a second, whereas uranium-235 is 710 million years. So that means it would take 710 million years for half of the atoms to decay. And then it would take another 710 million years for another half of those to decay over time. So what scientists can do then is that they can look at fossils. And as they look at those fossils, for the ones that are millions of years old or even billions of years old, they can look at the half-lives of, see how much of these elements are left in them. And since they know how long it takes for half of them to decay, they can kind of work backwards and see how old the fossil is. For younger fossils, they use carbon-14. So what happens is that plants take in the carbon dioxide, and that carbon remains in the plant, but after the plant dies, it stops making the carbon. So as soon as it dies, it stops taking the carbon begins to break down at a specific rate that is its half-life, and then scientists are able to calculate how many half-lives have passed since the plant died and estimate the age of the fossil. This process is called radioactive dating. So for example, if we just look at do the math here at the bottom, it tells us that data from a fossil of a mammoth tooth shows that carbon-14 has been decaying in the tooth for 5 half-lives. So if we know that there have been 5 half-lives, and we know from over here that the half-life is 5,730, so that means it's gone through 5 half-lives. Each half-life is 5,730 years. You do the math, and we find then that this fossil would be 28,650 years old. So that's how they use the half-life to determine the age of a fossil. So 5 half-lives. Each half-life takes 5,730 years. So this next part at the bottom is just sort of a challenge question. It's asking, what percentage of the original carbon is left in the fossil after 5 half-lives. So we would just take, 1/2 to the 5th. So 1/2 times 1/2 times 1/2. So what we're doing is we just keep cutting it in half. And if you imagine taking a sheet of paper, and you cut it in half, that would be the first half-life. And then you take that half a sheet of paper and cut it in half, that's the second half-life. Then you cut that in half, and that's the next half-life, and so on. So you just keep cutting your sheet of paper in half. So after 5 half-lives, you would have 1/32 of the sheet of paper. So if that were a fossil with carbon, you would have 1/32 the amount of carbon left in the fossil than was what was there originally. Sorry, got my tongue tied there. All right, On the next page, we're going to look at, very quickly, just a few other examples of how these radioactive elements can be used in science as well. Science uses these radioactive isotopes as what's called tracers in several different ways. Tracers mean that they basically put these isotopes in something, and then they are able to pick up on those and detect them with equipment to follow where the tracers have gone. In plants, obviously you're going to use non-radioactive forms of the element, but plants will take in phosphorus. So if they wanted to see how a plant is working, they could, the plant would absorb the radioactive phosphorus just like it would the regular phosphorus that's in the ground. So the scientists then can sort of put this radiation in the ground, and they can follow those tracers as they go through the plant, and they can detect them, and that way they can learn where and how the plants are using the phosphorus in their processes. Tracers can also be used to find weak spots in metal pipes or like in oil pipelines. So they can add these isotopes to a liquid, and then they can sort of monitor them and see them sort of light up, almost like an X-ray, as they leak out of the pipes. Since gamma rays can pass through metal and be detected by photographic film, gamma rays are also used to help look at structural damages in buildings and in bridges. So they can detect any cracks or weaknesses that there may be. You are probably familiar with the use of radioactive isotopes in the use of medicine. Sometimes they will use these, they'll put this element in the body, and then again it will light up using special tools so they can see if organs are functioning the way that they are supposed to. But most commonly, you're probably familiar with people who have had cancerous tumors sort of bombarded with gamma rays or radiation. So if you've known anyone who has had radiation treatments, that is a use of radioactive isotopes in the field of medicine. It's the gamma radiation that is being directed toward the cancerous tumor, and it kills off those cancer cells so that they can no longer function. And then lastly, nuclear energy is another use of radioactive isotopes. Remember, we said that there's nuclear fusion and nuclear fission when the nucleus of the atom either splits apart or fuses together. Both of those processes, fission and fusion, release huge amounts of energy when they react. That energy can then produce heat, well, it does produce heat, but it can be used to heat water and then use the steam in order to turn a turbine. So it's basically like using steam turbines, steam generators to get electricity, but it's just using nuclear fusion or fission as the source of energy to heat the water to create the stream. Alrighty, I would like for you then to just kind of go back, do any of the in-text questions that are left. Tomorrow I will have a Pear Deck review for you to work through. On Thursday we will do a little bit of review, and then on Friday you will have a Chapter 3 test that will cover all lessons in Chapter 3, so lessons 1 through 5. So you may want to start doing some review on your own and preparing for that test. Thanks, have a great day.